Greetings, everybody. Learning is a hobby here. I want to go over, as promised, my summary for chapter one, and also I think I'm gonna in this video do the solution set for chapter one as well because chapter one itself is kind of short. So we'll do chapter one and the solution set for chapter one in topics in commutative ring theory by J.J. Watkins. So let's bring up my notes here and we'll go through everything. Okay, here we go. So we start. Actually, before I even start on the definition of a ring here, uh, I mentioned it in the first video in this playlist that the book is kind of conversational. And what I have here, as always, it's a summary of the chapter. It's a very bare bones, just sort of, bullet point of what the important stuff in the chapter. But I suggest that you do read the book itself because he gives a lot of background and history and motivation for things that I'm not including um, in my summary here. So if you don't read the book yourself, you'll be missing out on a lot of the charm of the book. So I definitely recommend, actually reading through the actual chapter here. So that being said, let's get to the my summary. So we start with the definition of what we mean by a ring, and actually, in this book. Watkins says that really we'll only be considering commutative rings with identity, and we'll explain what that means here in the definition, because there is a more general concept of what a ring is. All right, so here's definition 1.1. A ring is a set R together with two operations on R, addition and multiplication. Here, R is not the set of real numbers. It's just a general set that has the ring structure. So these are the ring axioms here. One, addition must be associative. Two, addition has to be commutative. Three, R has to have a zero element, meaning an additive identity. It has to have additive inverses, meaning that if you have an element of the ring, then there should be an element that when you add A to that element, you get the additive identity. So an element that undoes the element, if you want to think of it that way, with respect to addition. Five, multiplication has to be associative. Six, multiplication has to distribute over addition. And here there's two distributive laws, one where we're multiplying on the left and one where we're multiplying on the right. And the reason we need two here is because an arbitrary ring is not necessarily commutative with respect to multiplication. So these six axioms that we have listed here, these are the ring axioms. But like I mentioned a minute ago, in Watkins' book, we're only really going to be considering rings that are also commutative with respect to addition and that also contain a multiplicative identity. Such a ring is called a commutative ring with identity, you know, creatively enough. So just a note here. The six axioms above define a ring, but we will concern ourselves in this book only with what I just said, with rings that satisfy the following two additional axioms. Thus, a commutative ring with identity is a ring R such that satisfies the previous six axioms, but also these next two. Multiplication has to be commutative, and also eight, R has to have a multiplicative identity, meaning, an element that when you multiply by it doesn't change the element. All right, so that's the definition of a ring, and then also a ring with a commutative ring with identity. All right, and we have some examples here. Here are some commutative examples. The integers are an example of a commutative ring, as well as the rationals, the real numbers, the complex numbers, and the polynomials with integer coefficients. There's a couple of non-commutative examples that I have here. The set of 2 by 2 matrices with real entries is an example of a non-commutative ring. The n by n matrices with complex entries are an example of a non-commutative ring. And then we also have an example of a commutative ring that does not have an identity, which is the set of even integers. All right, and then like I mentioned throughout the book, it's important to keep in mind that we will only consider commutative rings with identity. The theory of non-commutative rings has a very different character. If you watch the first video in this playlist, I mentioned some books on non-commutative ring theory. Right, but we're not going to be dealing with that in Watkins' book. Okay, so here's our first sort of theorem, I guess. The following three familiar rules of algebra still hold in an arbitrary ring R. All right, so there's three of them. One, zero time the when I say zero here, what I mean is I'm talking about an abstract entity here. It's the additive identity. So it's not necessarily the number zero, but we use the symbol zero to represent additive identities in algebra. All right, so zero times A has to equal zero for all A and R. Negative A times B has to be the same element as the additive inverse of A times B for all A, B, and R. And A times B minus C is equal to AB minus AC for all A, B, C, and R. And the proof we'll do in the problem set. So we'll do that in problem 1.2, which we'll do in this video, like I said, because this section is kind of short. Okay, just another note. There are certain subsets of a ring that are themselves rings with respect to the operations defined on R with the same identity as R. These are called subrings. So we have the definition of a subring here, which he calls this definition 1.2. Intuitively, a subring is just a subset of a larger ring that is also itself a ring under the operations from the bigger ring. But here, if you want to prove that a subset is a subring, then you could just show these properties in this definition. So a subset S of a ring R is a subring of R if S is closed under the addition and multiplication operations of R, contains additive inverses, and contains the multiplicative identity of R. So you just have to show those three things, and you're guaranteed that it's a subring. And then he says here in a note, problem 113 asks the reader to prove that definition 1.2 is equivalent to S satisfying definition 1.1. So in other words, if S is a subset of R for a larger ring R. So in other words, S is a ring in its own right under the operations of R. So that's basically the meat of chapter one, and I'm going to do the exercise set in the same video in a second. But let me just say something real quick before we move on to the exercise set. Um, we're going to do group theory on the channel in a little bit also, um, and also linear algebra. If you know anything about those subjects, for example, in linear algebra, subspaces are an important substructure of a vector space because they lead to, if you mod out by a subspace, you get something called a quotient space. In group theory, it's a little more complicated. You do want to look at subgroups of groups, but the important ones are the normal subgroups. If you mod out by a group, if you take a group mod a normal subgroup, you get a quotient group. In ring theory, we want to be able to do the same, build the same type of quotient structures, but it's not a subring that you want to quotient out by. It's actually something called an ideal. You want to mod out by an ideal, and if you do that, then you get something called a quotient ring. Um, we'll look at that. We'll look at ideals and quotient rings in chapter two of the book, but just to mention that here while we have the definition of subring, subrings are not really the important substructure of a ring. It's the ideals that are sort of the really important ones. Anyway, let's get to the exercises here. So I did all of the exercises. There are only 13 problems, and they're all kind of short or very pretty straightforward. So I'll just go through them kind of quickly here. And again, I'll just mention it here. The PDFs that I'm going over here are available on the Patreon page. You just have to become a member. It's $3 a month. Um, Okay, so question 1.1. Show that in a ring, the zero element, the multiplicative identity, and additive inverses are each unique. We've done this before for fields in Spivak, for example, but the proofs are very similar here in ring for a ring. Uh, fields are an example of a ring too, but they have additional structure than just the ring structure. I'm not going to get ahead of myself here, so let's just do this here. Okay, part A. The zero element is unique. So let 0 and 0 prime be elements of the ring R, be zero elements of R, then zero is equal to zero plus zero prime, which is also equal to zero prime plus zero. Again, addition is commutative in a ring, so which is equal to zero prime by axiom three. So zero equals zero prime, so therefore zero elements are unique. And we do a similar proof for multiplicative identities, so I won't. You could look at it here. It's virtually the same proof, except with respect to the multiplicative identities and multiplication. So here you can see that multiplicative identities are also unique if they exist, right? And then C, additive inverses are unique as well. Let A and R and B prime be additive inverses of A. Then B equals B plus zero equals B plus A plus B prime, which is equal to, by associativity, is equal to B plus A plus B prime. And then by commutativity of addition is equal to A plus B prime, which is equal to zero plus B prime, which again by commutativity of addition is B prime plus zero, which is B prime, so B equals B prime, so additive inverses are unique. Okay, question 1.2. Use the 8-ring axioms to prove the 3 familiar rules of algebra 1 through 3 listed on page 7 of chapter 1. That was like the only real theorem that we had in chapter 1, which we talked about a few minutes back. Of course, B minus, he says here, the author, B minus C is simply a convenient shorthand for B plus the additive inverse of C. Okay, so let's do them one at a time. Part A, we want to show that 0 times A equals 0 for all A and R. And then again, just to remind you, when I say 0 or 1 in this book, or in ring theory in general, or even in group theory, I don't necessarily mean the number 0 or the number 1. We mean the additive identity and the multiplicative identity, which may be some other object than the number 0 or the number 1. Just to get that out there. Okay, so we want to show this. Then here's my proof. 0 times A plus 0 times A is equal to 0 plus 0A by the distributive law, which is equal to 0 times A. That's because 0 plus 0 is equal to 0 because it's the additive identity. And then we can add multiplicative inverses of 0A to both sides. Sorry, I got a hair in my mouth. Okay. Um, and then using associativity on the left-hand side, that's equal to 0 times A plus 0A plus minus 0A. And on the right-hand side, we're adding additive inverses, which gives you the additive identity 0. And 0A plus negative 0A also is 0. So we get 0A plus 0 equals 0, which implies that 0 times A is 0. I should say here also, we can do a similar proof to show that A times 0 equals 0 for all A and R as well, which will be relevant in a few minutes. But I didn't prove that here, but you can do virtually an identical argument for that. Okay, part B, negative A times B is equal to the additive inverse of A times B. When I say negative here, again, I should be careful. What I mean is the additive inverse of A times B is equal to the additive inverse of AB, the element A times B. All right, and here's my proof. AB plus the additive inverse of A times B equals, by the distributive law, A times the additive inverse of A times B, which is 0 times B, which is 0 by part A, which implies that the additive inverse of A times B is equal to the additive inverse of AB by problem 1.1. Right, then part C, we want to show that A times B minus C is equal to AB minus AC. Right, so here's my proof. A times B minus C, it means A times B plus the additive inverse of C, which is equal to AB plus A times the additive inverse of C by the distributive law, which is equal to AB plus A times, oh, did I write that twice? I don't know why I did that. I didn't need to write this again. Right. Then just a note here, using similar proofs as above, it can be shown that in an arbitrary ring, it's also true that B times 0 equals 0 for all B and R, and also that A times minus C equals A times the additive inverse of C equals the additive inverse of AC for all A, C, and R. I didn't prove that, but you can do it virtually. It's a virtually an identical proof to the ones that we already did. Also, if you assume that we're working in a commutative ring, really it's arbitrary because we're already assuming that multiplication is commutative. But I want the theorem says for an arbitrary ring, so I didn't want to assume commutativity for this one. All right, so that implies that AB plus A times the additive inverse of minus C equals AB plus the additive inverse of AC equals AB minus AC, and that's the proof. All right, question 1.3, let R be a ring and let AB be elements of the ring R. Prove that the additive inverse of A times the additive inverse of B is equal to AB. And here's the proof. The additive inverse of A times the additive inverse of B plus the additive inverse of AB equals the additive inverse of A times the additive inverse of B plus A times the additive inverse of B, which is equal to, by the distributive law, the additive inverse of A plus A times the additive inverse of B, which is equal to 0 times the additive inverse of B, which is 0, which implies that the proposition is true by theorem 1, right? 1.1, because its additive inverses are unique. Okay, 1.4. Let R be a ring and let A be an element of the ring. We can inductively define powers of A as follows. A to the 0 is 1, and A to the n equals A to the n minus 1 times A for n greater than 0. Use induction on n, fixing m as necessary to prove that these three properties of exponents hold in an arbitrary ring. We're assuming commutativity here, so I'm going to assume we're in a commutative ring, because otherwise these are not necessarily uh, things don't necessarily work out the same way. Okay, so AB to the nth power is AN times B to the n. Then we also want to show A to the m times A to the n is equal to A to the m plus n, and A to the m to the n is A to the mn for any non-negative integers m and n. And then just a note, we haven't defined A inverse, which is the multiplicative inverse of an element A of a ring, since multiplicative inverses may not exist for every element in an arbitrary ring. Testing, testing, testing. Testing, testing, testing. Testing, testing, testing. Testing, testing, testing. Testing, 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 testing. All right, sorry about that pause, guys. It looks like I was having some audio issues with my microphone. Hopefully, hopefully the what I went through so far was recorded. I guess I'll have to go back and see if it isn't. But I'm going to continue here just in case it did work out, so I don't have to record that whole part over again. Okay, so we where did we leave off? Uh, Maybe I'll read this note again. So we haven't defined the multiplicative inverse of A, since multiplicative inverses may not exist for every element in an arbitrary ring. So for example, the integers are a ring. 2 is an integer, but 1/2, which is its multiplicative inverse, is not an element of the ring. So for example, rings may not be closed under taking in multiplicative inverses. Okay, so here's the proof of the first one. So AB to the 0 power, by definition, where that's equal to 1, which is equal to 1 times 1, which is A to the 0 times B to the 0 by definition. All right, then we get to the inductive step. Assume there is an n in Z, n greater than or equal to 0. Sorry, this should be an arbitrary ring, right? Oh no, sorry, the powers are positive integers. Sorry, A and B are elements of an arbitrary ring. Assume that. Sorry, the microphone thing threw me off a little bit. Assume there is an integer n, a non-negative integer n, such that a to the b to the n equals a to the n times b to the n. Then consider ab to the n plus 1. That's equal to ab to the n times ab by that recursive formula, which is equal to a to the n b to the n times a times b, by the recursive formula, which is a to the n times a times b to the n times b, because we're assuming that we're working in a commutative ring, which is equal to a to the n plus 1 times b to the n plus 1, and that's the inductive proof. Right, then we prove the second property. Fix m and z, m greater than or equal to 0, and induct on n. The base step, a to the m times a to the 0, is a to the m times 1, which is a to the m, which is the same thing as a to the m plus 0. So the base step is satisfied. Then go to the inductive step. Assume a to the m times a to the n is a to the m plus n for some non-negative integer n, and consider a to the m times a to the n plus 1. That's equal to a to the m times a to the n times a by the recursive formula, which is equal to a to the m plus n times a, which is equal to a to the m plus n plus 1, and that the inductive step follows, which means that the property holds for all non-negative integers. Right, and then lastly, property number 3, fix m and z, m greater than or equal to 0, and then induct on on n. All right, the base step, uh, a to the m to the 0 is 1 by definition, which equals a to the 0, which equals a to the m times 0, so the base step is satisfied. Then we go to the inductive step, assume a to the m to the n is a to the mn for some non-negative integer n, and consider a to the m to the n plus 1. That's a to the m to the n times a to the m, which is equal to a to the mn times a to the m, again by the recursive formula, which is equal to a to the mn plus m, which is equal to a to the m times n plus 1. So that holds by induction as well. Okay, question 1.5, let R be a ring such that 1 equals 0, where 0 is the 0 element, and 1 is the multiplicative identity in the ring. Show that R consists of just a single element. And then Niven said, sorry, not Niven, Watkins says you should convince yourself that conversely that the set R equals the singleton, just the additive identity here, where the operations addition and multiplication are defined by 0 plus 0 equals 0, and 0 times 0 equals 0 is actually a ring by verifying all the axioms. This rather trivial yet not altogether uninteresting example of a ring is called the zero ring. All right, so here's the proof that if 0 equals 1, then all the elements are just 0. So let A be an arbitrary element of the ring R, and we're assuming the hypothesis that 0 equals 1. Then A equals A times 1 equals A times 0, because we're assuming 1 equals 0, which is equal to 0. So that shows that every element is just the additive identity 0. All right, and then we show that the zero ring is also a ring. So that if you take R with being the set that just contains the element zero, and you define addition the way that he said and multiplication the way that he said, then if you look, all of 8 of the axioms are satisfied. So I won't go through this in detail because it's pretty straightforward, but you can see here all the axioms work. All right, 1.6, we define the set Z times Z. This means Cartesian product, right? It's a set of all ordered pairs A comma B, where A and B are integers. Show how to make the Cartesian product into a ring by suitably defining addition and multiplication. What is the zero element? What is the multiplicative identity? Again, this is pretty straightforward. We define A the sum AB of the ordered pair AB with CD to just be the component-wise addition, and same thing for multiplication. We do it component-wise, and then the zero element is just the ordered pair 0 comma 0, and the identity, the multiplicative identity, is just the ordered pair 1 comma 1. And you could check all the axioms. I didn't do it here, but it works. Okay, 1.7, assuming that the set of real numbers R is a ring, show that the complex numbers form a ring with operations that defined here. So it's the usual addition and multiplication of complex numbers. All right, and I went through the process here of verifying all of the axioms. I won't belabor the point here. You could stop your screen, pause the video here if you want to see them. But we've done this a bunch of times in other videos and stuff. So I'm just verifying that the 8 axioms are satisfied. So, like I said, I'll just scroll through this really quick. And if you want to, see the details, like I said, the PDFs of these are available on the Patreon page. Okay, so all 8 axioms are satisfied for the complex numbers. So it's a ring, a commutative ring with identity. Right, 1.8, is 2Z a subring of Z? And actually the answer to this is no, because one, the multiplicative identity is not in the set 2Z. The other two parts of the definition 1.2 are satisfied. It's closed, the set 2Z is closed under addition and multiplication. It also contains additive inverses, but it doesn't contain the multiplicative identity, so it's not a subring. All right, 1.9, do the rationals form a subring of the reals? And here the answer is yes, because all 3 properties specified in definition 1.2 are satisfied. So like I said, here you can pause your screen and see this is pretty straightforward. So yes, Q is a subring of R. 110, does the set of all numbers of the form A plus B radical 3, where A, B, and Q, meaning the rational numbers, form a subring of the reals? Here again, the answer is yes. You just show that the 3 properties in definition 1.2 are satisfied. Here they are, so it's a subring. All right, 111, do the reals form a subring of the complex numbers? Again, the answer here is yes. All I did was just show that the 3 properties of definition 1.2 are satisfied. Again, you can pause your screen if you want to see that. It's pretty straightforward. 112, does the set of all numbers of the form A plus IB, where A and B are integers, form a subring of the complex numbers? This one also, the answer is yes. And again, I just showed that the 3 properties are satisfied in definition 112. Right. And then lastly, the last problem in the problem set is 113. Let S be a subset of a ring R. Show that if S is a subring by definition 1.2, then S is itself a ring. Right. So let S be a subset of the ring R, and S satisfy definition 1.2. Then S is a subset of R, implies the ring axioms 1, 2, 5, 6, and 7 are satisfied, right? Because we're taking elements of a ring already. So obviously, the associative laws and so on are all satisfied. Next, if A is an element of S, then negative A is an S by definition 1.2. This implies that the additive identity is in the set because A plus negative A is 0, and it's an element of S because S is closed under the operations of the bigger set, the bigger ring, right? Since S is closed under addition, that implies axiom 3 and 4 are satisfied. Lastly, axiom 8 is satisfied by definition 1.2 directly. Therefore, S is itself a ring under the operations of R. And that's it. That's chapter 1. So let me stop my screen share. Hopefully, the audio issues were didn't affect the first part of the video, which I'm worried about, but I'll go back and check and see. If not, you won't see this video. If it didn't affect it, then you know, you'll be seeing me worrying over this. Okay, so I am going to be continuing with this book. The next chapter two is on ideals and quotient rings. I'll see you in that one. Let me know what you think down below, and I'll see you guys in the next video.